Dear students, welcome to today's online class. Today we discuss close packing of spheres or the particles in crystals, and here we consider metallic crystals. See, there are two ways of looking at crystal structure. One is like this. We emphasize the geometry of the crystal. This is of course cubic crystal, and the particles or the motifs are shown very small, or we just show the lattice points so that we can appreciate the geometry of the crystal. Actually, the state of affair is that these particles are rather big, so big that they almost touch each other. That is the actual state of affair. Close packing is there. So the second way of looking at the structure of a crystal is showing the particles as they are. That means big enough to touch each other. So that is what is close packing. So for example, if you look at this is again a cubic crystal where the particles are shown big so that they are touching each other, right? If we show them so small or as a lattice point and join them, we get a cubic crystal shape. Okay, so in this discussion we are considering this aspect of crystals, that is close packing. Close packing of spheres. Why spheres? It is assumed that the motifs in the crystal, the constant particle, which may be atom, ion or molecule, they are roughly spherical in shape. Atoms are spherical in shape, and we assume that they are hard spheres. Okay, and so we are considering how these spheres are arranged closely. There are some assumptions here that when these spheres are hard and impenetrable, so they will touch at a point when they are closely packed. So this is how the particles are arranged in close packing. And again, when we consider close packing, we will see what are the different types of close packing possible in crystals. Again, another assumption is that here, since we are considering only metallic crystals in this discussion, of course we will consider ionic crystals in later in another class. What is the speciality of metallic crystal? They contain only one type of particle. That means all spheres are identical, same size, they are having same size. Only one type of particle is there. So let us arrange these spheres in maximum close manner, most closely, most efficiently. So when you go for a close packing, the policy will be that each particle or each sphere will be in touch to the other particle, and maximum number of particles are arranged around. That is called coordination number. The number of neighboring particles immediately around each particle. So to have maximum stability for the crystal, each particle will have maximum neighbors around, making use of maximum space, leaving out very little or minimum empty space, maximum space utilization. So each particle will have maximum neighbors around, so that there will be more attraction and there will be more stability. Okay, so keeping these points in mind, let us go to the close packing in metallic crystal. Okay, here the blue sphere, this is sphere actually, we are drawing of course on a 2D plane, you have to understand. The blue sphere, you can see, consider the spheres which are arranged one to the next in touch. Okay, so this represents a row of spheres. If you just show the lattice point as the center of the sphere, you will get one point here, then next one, you can see equidistant point repeating regularly. That is the crystal lattice. This is one-dimensional lattice. We can call this as a row. And this is a situation, if you consider edge of a crystal, if this is a crystal, the edge will have this kind of arrangement. Particles are touching each other. So that is the first row. This is first row. Now, so this is a 1D lattice. Now going to the 2D lattice, that means now different rows are arranged side by side. So the second row is placed how? In between the particles of the first row. Between these two we keep the first particle of the second row. Like that we keep. So that particles are maximum close, leaving out minimum empty space. Maximum stability. So this is the second row, keeping particles in the depression created by the two particles. And that is repeated. Okay. So this represents 2D lattice, or this is a layer. Okay. That is the situation of a face or a plane of a crystal. For this crystal, if you consider one face or a plane, this will be the situation. Particles will be arranged in this manner. So let us call this blue spheres, the whole blue spheres arranged in one layer, and that is first layer. Suppose this is the first layer, the blue layer. Okay, and that is a 2D lattice. Now what about a crystal? In crystals, these kinds of layers are arranged one above the other. Then comes 3D lattice. Correct? So the blue layer is there. Above that we will keep the second layer, third layer, fourth layer, etc. That build up the crystal. Now in all crystal, arrangement of first layer is like this. Okay, let us now consider the placing of second layer. For that, you have to consider the depressions seen in the first layer. See, when we keep these three particles, okay, in the first layer, you can see a depression coming at the middle of three touching spheres. You can see there are depressions everywhere. I have classified these depressions into two. This is marked as 1. This is 1. This is 1. All these are 1. Okay. And below you can see along two rows you can see depressions above and below. The below one is marked 2. This is 2. These are all 2. These are all 2. Okay. So two sets of depressions are there in every layer. Okay. Now that it is like this. You can look at this model. Right. This is how. First row, second row, there will be third row, all those rows, and this is first layer. You can see that here, you can see depressions at the center of three spheres. You can see depressions everywhere. And this is 1 and these are 2, above and below. And interestingly, if you keep a particle in the second row, how you keep, the second layer, particles in the second layer, above the first layer, you will keep at the middle. At the depression, of course, right? Now, you can see that I have shown the second layer as using green color, right? As a broken line, that is the second layer. You see that I have kept in this diagram the second layer, particles are kept above the depression set to 1. See, above 1 I have drawn this green. Here also above 1, it goes like this. You can see, so this is the first row of the second layer, the green spheres. And in the second row, you can see that the green sphere is again above 1. Right? All above 1. What does it mean? When you keep the second layer above the first layer, if you keep the particles above one of the depressions at 1, 2 remain unoccupied. If you keep above 2, then 1 will be unoccupied, of course. So, this green sphere is second layer, right? So now this is the situation in all crystals. Okay, let me mark this first layer as A, the second layer as B, suppose. Now the difference comes in the third layer. The third layer can be arranged in two ways. One, the first type is that, okay, now you have to think about the depressions above the second layer of, right? So what are the depressions above the particles above the second layer? See, we are going to keep the third layer above the second layer. So you have to consider the depressions on the second layer. You can see, if you take the green spheres, suppose these two rows you consider, that is only drawn here. You can see one depression is that this depression number 2 is there. That is the depression which remain unoccupied from the first row layer itself. That is the one. And the second one is a new depression created, that I have marked as 2 dash. Okay, so this 2 dash, like that it goes. So depression number 2, which remain unoccupied from the first layer, that is the one set of depression, and depression number 2 dash is the second set of depression. So when I keep the third layer above the second layer, I have two options. Either to keep the particles above this 2 dash. See, if I am keeping the particles of the third layer above this 2 dash depression, which is the new depression appeared, how does it look then? If I keep a particle exactly above 2 dash, you can see that is exactly above the first layer. See, this blue, correct? This blue sphere. If I keep a particle above 2 dash, this particle will be exactly above this blue sphere. That means it will come like that. That means here the third layer is exactly above first layer. Okay, the third layer come exactly above first layer, that we call again A. Then the fourth will be exactly above the second layer automatically. So the pattern will be AB, etc. type. That is known as hexagonal close packing. Hexagonal close packing, or abbreviated HCP. So this is one type of close packing in some of the crystals. HCP, we can call it AB, etc. type. So what is the speciality of this HCP? The third layer is kept exactly above the first layer, so that AB pattern repeats. Example for these crystals are alkaline earth metals like beryllium, magnesium. Similarly, D block metals like zinc, cadmium, etc. fall under this category. For this HCP close packing, see the coordination number. What is coordination number? The number of particles around touching a given particle in the crystal lattice. You can see it is 12. Right? This maximum efficient packing. This number you may remember, that is in FCC also we have seen that coordination number is 12. And the packing efficiency is also, you can see, the packing efficiency of this is 74%. That is again the same as this FCC, 74%. Okay. Then effective number of particles per unit cell. If you take the unit cell of HCP, that is obtained like this. In the first layer you consider the blue spheres, these ones 1, 2, 3, 4, 5, 6. Okay, and one at the center. And above that first layer you can see in the second layer touching particles, that is these 3, 1, 2, 3. Okay, and then the third layer you will have the same 6 particles like this coming above, and also one at the center. If you take that portion, if you cut out that portion from this that will represent the HCP unit cell. And if you calculate the effective number of particles, you will find it is 6. That is the case of HCP. Now the second type of close packing is that you are keeping the third layer in a different way. In HCP, we are keeping the third layer exactly. I'm not drawing the third layer because that will make it very confused. So just you have to explain. The third layer is kept exactly above the first layer, then it is HCP. Now the other option is what? I am keeping the third layer not above first layer, or I am keeping the third layer particles on the depression number 2. In HCP it is about 2 dash, so that it came above first layer. If I am keeping the third layer particles above this depression number 2, which is the depression which remain unoccupied right from the first layer, right? If I draw a sphere here, you can see that this sphere is not above first layer nor second layer. It's a new layer. So we have to mark it C, layer C. And if you go for the fourth layer, interestingly we will see that the fourth layer particles will automatically come exactly above first. And the fifth layer will come exactly above second and continues. This kind of close packing is called cubic close packing. Cubic close packing or CCP. So if the first layer is A, the second is B, the third is C, and the fourth, and it will repeat ABC type. Right? CCP, cubic close packing. And here coordination number in this case is again 12. Packing efficiency is again 74%. But the effective number of particles is 4. And you know that effective number of particles is 4 in the case of FCC. FCC is a face-centered cubic lattice. That is one of the bravest lattice in cubic system, which is a different perspective of the crystal structure. As I said earlier, looking at the position of the lattice points in the cubic crystal, where we emphasize the geometry. And here we are considering the close packing, but it is interesting, so interesting that CCP is in close examination, you can see that CCP is one and the same as FCC. This is nothing but FCC. That's why it is 4. You can see that both HCP and CCP are equally efficient. Both are having 74%. And naturally coordination number is also same. But since the unit cells look different, here it is 6 but here it is 4. How you verify? Okay, coming to examples. In the alkaline earth metals like calcium, strontium, they are having CCP arrangement. Similarly, silver, gold, etc. D block metals, these are all CCP. Okay. Now, I told you that CCP is the same as FCC. They are one and the same. We can verify using this model. See, you know this is FCC. I have shown it earlier. There are particles at the 8 corners and at the face center also. If I hold it like this, okay, and if I show different colors, for example, consider this particle, okay, the bottommost particle, this one. Only one particle, like, because it's a unit cell, of course it will repeat in this layer. So this is layer number 1, A. This second layer, okay, this is the second layer, that is layer number B. This is the third layer. You can see that particles in these layers A, B, C, none of them are exactly above. They are not aligned. All are different. But if you take the fourth layer particle, only one is shown here. This particle you can see, this is exactly above this one. So if this is A, this is again A. Of course it will be continued all over. Okay, but we have taken only the unit cell part here. So the point is that this CCP is the same as FCC. This is FCC. Okay, FCC is the same as CCP in close examination. They are one and the same. Okay, so that's about the close packing of particles, mainly these two types. In addition to this HCP and CCP, there is one more type of close packing, that is BCCP. You know what is BCCP? If I just show using the unit cell diagram, what is BCC? Body centered cubic. So there are some crystals like iron, tungsten, and also metals like vanadium, similarly barium. Okay, these metals. So this is the third type of close packing, that is called BCCP. BCCP means body centered cubic close packing. Body centered cubic close packing. Okay, here it is that the particles are there all at the corners. Of course, they'll be touching each other. I'm not showing exactly as it is, and there will be particle one at the center also. So it is having a BCC arrangement, and here, you know, in BCC packing efficiency is less. It's only 68%. Coordination number is only 8. Effective number of particle is only 2. Naturally, it is less efficient. That is why metals like barium, iron, chromium, tungsten, these metals are found to be much lighter, density is less because of this reason, because they are not having this arrangement, but they are having body centered cubic close packing. That's why. So that's about different types of close packing in metallic crystal. And in the next class, we will understand another important concept in crystal structure, that is about the empty space which are present in this close packing. They are called voids or interstitial voids in the next video. Thank you.